Structure of a virus. To investigate the structure of extremely small objects, the wavelength of the probing wave should be about 1/10 the size of the object for sharp images. But as the wavelength gets shorter, the energy of a photon of light gets greater and could damage or destroy the object being studied. One alternative is to use electron matter waves instead of light. Viruses vary considerably in size, but 50 nanometers is not unusual. Suppose you want to study such a virus using a wavelength 5 nanometers. Part A. If you use light of this wavelength, what would be the energy in electron volts of a single photon? And part B. If you use an electron of this wavelength, what would be its kinetic energy in electron volts? Is it now clear why matter waves such as in the electron microscope are often preferable to electromagnetic waves for studying microscopic objects? Okay, so in part A, we're calculating the energy of a photon that has 5 nanometers wavelength. The energy of the photon is hc divided by lambda, the wavelength, which is 1243 electron volt nanometers divided by the wavelength in nanometers. So if we put 5 nanometers for the wavelength, it's 1243 divided by 5. This gives us a photon energy, E photon, to be 249 electron volts. Now we're repeating this exercise for an electron. Okay, so the free electron energy is its momentum squared divided by 2m, purely kinetic energy, which is equal to h bar square k square divided by 2m. K is the wave vector. So this is Planck's constant h square divided by, because h bar is h divided by 2 pi, h bar square is h square divided by 4 pi. Multiplied by 2m, it's 4 pi square, so it's 8m pi squared, and then we have k squared, k is 2 pi over lambda, so it is 4 pi squared divided by lambda squared. And now we can see that pi squares will cancel out, and then we have 4 making this 8 2, so we have the final electron energy h squared divided by 2m lambda squared. So here our wave vector k has a magnitude 2 pi over lambda, and the electron momentum p is h bar times k, the wave vector k. This is actually a vector equation. Okay, now we can plug in the numbers to calculate the electron energy. Electron energy is Planck's constant squared, which is 6.63 10 to minus 34 joule seconds squared, divided by 2 mass of the electron 9.11 10 to minus 31 kilograms times 5 nanometer 5 10 to minus 9 squared. And if I divide this number by the electron charge, I will have it in units of eV. So I will divide it by the electron charge, 1.6 10 to minus 19 coulombs. So I obtain the electron energy to be 60.3 milli electron volts. Okay, so as you can see, this energy is much less than that of the photon with the same wavelength. So we have the conclusion, since the electron deposits much less energy, so the electron causes much less damage to the virus under study. Okay, so in this problem we have compared the matter waves, electrons and photons with the same wavelength in order to probe the structure of a virus, which is 50 nanometers in size. And as a rule of thumb, 1/10 of the size of the object is a good number to get a sharp image. So we're looking for a wavelength of 5 nanometers. The photon energy is hc over lambda. The electron energy is h bar square k square over 2m. So where k is 2 pi over lambda, if we substitute the numbers, we indeed find that the electron energy corresponding to the same wavelength is much less than that of the photon, so it is better to use the electron microscope in order to image the structure of a virus.